This lesson is on simplifying rational expressions. It will provide you with yet another use for factoring polynomials. Before we look into rational expressions, let's just look back at what rational numbers were. Rational numbers were essentially fractions. So, for example, you could have 2 over 6. That is a rational number. However, this rational number is not in simplest form. Recall how we simplified. Well, one way that we learned to simplify was to look at common factors. So 2 is its own, it's a prime number, it cannot be further factored. 6 could be factored into 2 times 3. When you have products like this, you can notice that you may simplify because you can divide numerator and denominator by the same factor, leaving you with 1 over 3. So this is simplified form, but 2/6 is equivalent to 1/3. So we're going to be looking at simplifying rational expressions as well as looking at for when they are undefined. So when was a rational number undefined? Well, it was not defined when the denominator was 0. You could have a number, but if you had 0 in the denominator, the fraction was undefined. So those two key points we are going to apply to rational expressions. What are rational expressions? Well, just like fractions, they are a quotient of polynomials. So essentially, we're making a fraction out of polynomials. Here are some examples of rational expressions. So our 2 points that we're looking at are simplifying, and we're looking at what makes the denominator undefined, and that relates to the domain of the rational expression. If you can recall, domain was the possible inputs for the variable. So let's just explore with these before we set out and create any rules for us to follow. In this first example, you can see that the numerator and denominator are completely factored, and so nothing can be further simplified. Same goes with the next one, although it is very common for people to want to cancel these x's out. But remember, you can only cancel things out if they are multiplied together, because then you can divide them out. Multiplication and division are opposites, whereas subtraction is not opposed by a division. So really be careful. One example here would be, say you had 2 over 2 plus 4. Could you say that you could cancel those out? Those 2's? Would that be 1/4? Well, we know this to be 2 over 6, which is 1/3, which is not equal. So you cannot cancel when you have a plus. So this cannot be further simplified. This next example, are the numerator and denominator fully factored? Remember, when we were simplifying rational numbers, we factored first and then divided by common factors. Here, the numerator is factored completely. However, the denominator could be factored further. So you could have a minus 3 over, notice that a squared minus 9 is indeed a special factoring formula called the difference of squares, resulting in a minus 3 and a plus 3. Now we have a common factor which we may divide both numerator and denominator by. So a minus 3 is the common factor. So a simplified but equivalent form of a minus 3 over a squared minus 9 would be 1 over a plus 3. So this is simplified form. Let's keep going here In this next example, we have x minus 1 over 1 minus x. So they seem like they could be the same, but they're not quite the same. Why don't we try to rearrange it so that our variable comes first, and therefore we could factor the denominator, factor a negative out of the denominator. What would happen if you factored a negative out? You'd have a positive x and a negative 1. Remember, when you factor negatives out, it switches the order in a subtraction. Now we have the same factor. So these could divide both numerator by denominator, but they don't disappear. Think about what you've done. You've divided them by x minus 1, numerator and denominator, leaving you with a 1 and a 1, leaving you with a negative 1. So this is a simpler way of writing this, but it is also an equivalent format. Now, for the second point, stating the restrictions. What possible problems could we have with x here? Well, remember that we have problems with our domain when the denominator is 0. Therefore, our denominator cannot equal 0. So, in our case, x cannot equal 0. That is our one restriction for x, and everything else works. How about here? When does x make x minus 2 0? Well, we can just write it out as an equation and solve. So when x is 2, our denominator is 0. Therefore, x cannot be 2 for this rational expression. In the third example, it gets a little more complicated because we always want to take the restrictions from the original equation, not the final equation, because we've lost something that in the original would have caused a problem. So, if you want to find restrictions for this one, you'd want to see when a squared minus 9 equals 0. And this goes back to solving quadratic equations, where we factored it and considered each bracket separately. So a would equal either 3 or negative 3. You can see that if you squared 3 minus 9 or squared negative 3 minus 9, you'd still get 0 both times. So don't forget to say that a cannot equal 3 or negative 3. Now, what would the restriction be here? From the original, 1 minus x could not be 0. So we could solve this. We could just add x to both sides. We get x does not equal 1. Even though the answer is negative 1 in simplified form, the variable in the original question was restricted to all real numbers except for positive 1. So let's sum these things up. Rational expressions are not defined when the values of the variable make the denominator equal to 0. Common factors may be reduced in order to rewrite the rational expression in a simpler but equivalent form. However, you want to be careful not to cancel out items that are non-factors. So, make sure that when you are canceling out, those items are attached with a multiplication symbol to the rest of the level. Let's continue to some examples. Here, all they ask us to do is figure out what values make the expression undefined. Therefore, we're looking for restrictions on the domain. So all we're interested in is the denominator. When is the denominator equal to 0? We can't make it equal to 0, so we say not equal to 0. So this is just solving an equation. Solving an equation with a square, we need to factor. And notice that the leading coefficient is 1, so we can factor directly. Two numbers that multiply to 7 and add to 8 is 1 times 7, and 1 plus 7 gives us 8. Therefore, x is either -1 or -7 when you use the zero property. You can justify that for yourself. So x cannot be -1 or -7. In the next example, we have no x variables in the denominator. So we have no values for which this expression is undefined. In the next example, you can see that x plus 3 is 0 when x is -3. Therefore, x cannot be -3. Similarly, in this one, 3x plus 5 is 0 when x is -5/3. Therefore, x cannot be -5/3. The following examples ask us to simplify each expression. So first, we want to make sure that the numerator and the denominator are completely factored. In this case, they are. There are no pluses or minuses that are loose, and this is actually a type of problem that we've seen before. So let's just try it again here. So 25 over 10 can simplify by dividing by the common factor of 5, leaving us with 5 over 2. Then we have x to the power of 2 over x to the power of 1, leaving us with an x on top. And we have a y and 3 y's in the bottom, leaving us with 2 y's in the bottom. You could do this by subtracting. You'd notice you'd get 1 minus 3, leaving us with y to the -2 in the numerator, which would then go to the denominator as y squared. So the restrictions here would be x does not equal 0 and y does not equal 0. However, they're not asking for the restrictions, so they're just asking us to simplify. The next problem, we want to make sure that you have factored completely, and then once you have done so, you also want to make sure that you have decreasing exponential order. Once you've factored completely, notice that we are simplifying common factors. So, in the numerator, we want to make sure the x squared term is first. So let's just rewrite it first to see how that looks. And the denominator is like this. We also like to get the negative out of the leading coefficient, because then it's easier to see if anything is the same. So that would leave us with x squared minus 4 over x squared minus 4. Now we could completely factor these and use the difference of squares, but if they are the same right away, then hey, divide by them. You're left with -1 over 1, which is -1. Notice that if you had to restate the restrictions here, x squared minus 4 cannot equal 0. Now, since this is a square, you want to factor this using the difference of squares formula, which leaves us with x does not equal 2 or -2. Here are some more examples. They're asking us to simplify, and we can also state the restrictions as well. So as before, we want to make sure everything is completely factored so that we may notice if there are any common factors. So in the numerator, we can start by taking out the greatest common factor, which is 2a, leaving us with a minus 4. Let's check that. 2a times a, 2a squared, 2a times -4 is -8a. The bottom one does not have a greatest common factor, and it's a trinomial. There are no perfect squares, so it's not a special formula, and there's no leading coefficient, so we don't need to do decomposition here. We can just factor directly. So we've got a's, and we're looking for two numbers that multiply to 8 and add up to -6. So we could have 1 times 8, 2 times 4, and that's about it. So 2 and 4 add up to -6. If they were both negative, they would also multiply to a positive. -2, -4. You can check that. And then we look for any common factors. So before we cancel, it's a good idea to state restrictions. We know that a squared minus 6a plus 8 cannot be 0. Therefore, to solve that, we would also factor similarly as we just did, and that would leave us with a not being 2 or 4. But when we simplify to something, we can see that the a minus 4 term is common and it is a factor, so we can eliminate it, leaving us with 2a over a minus 2, and I believe there are no other common factors. Notice that a is a factor of the numerator, but it is not a factor of the denominator, so please don't cancel it. And let's look at the last example over here. Because we've got some expanding to do, let's do that first. X squared minus 6x plus 9 over 9 minus x squared. And note that because you want your x squares first, let's just rewrite that in order. We also want leading coefficients to be positive, so let's factor out a negative, leaving us with negative x squared minus 9. Hopefully you're starting to see the reasons for these rules that seemed a little bit arbitrary at the beginning, because our goal is to see that the factors are common, and the only way to see them to be the same is if they are ordered in the same manner. The numerator is a trinomial, and we've actually got perfect squares. So you can see that this here is a 3 squared and this here is an x squared. So you could use the perfect square trinomial formula. You could also use the direct factoring. What times what is 9? That adds to -6. Well, you'd have x minus 3 times x minus 3. So it'd be x minus 3 squared. However, for the purposes of simplifying, we could write it out just to make it a little clearer to see how many of those cancel. The denominator here is actually a difference of squares. So let's write that out as well. We want to make sure that everything is completely factored. Maybe I'll just write this here as a square so that you see it could be written like this or like this. Alright, so what common factor do you see here? Yes, the x minus 3 term can be divided from the numerator and the denominator, leaving us with x minus 3 over negative bracket x plus 3. Now there are a few different ways of writing this. You could write or negative outside like this, and that would be also fine. Or you could write brackets on both numerator and the denominator. You could even put the negative in. There's a bunch of ways, but you'll most commonly see it written like this. Now if we had to state the restrictions, 9 minus x squared is equal to 0 when, and we can look at our completely factored form before simplification. Because that is essentially the same thing, just factored, and each factor could be potentially equal to 0, leaving us with x not being 3 or negative 3 as our restriction on the domain.